crystallizing of differential forms. Not the differential forms with the square root.
So the same.
Well, it will be the bit. Okay? Because, yes, the differential forms in Cartan, in color, in the baby reading books, and other people, okay, are functions, one forms, functions of curves, not linear values. I'm not saying anything wrong. What I'm saying is there is another concept, okay, and that is important to realize, and that's the reason why color, okay, normally when we have components of our mathematical numbers, there are two series of indices. Color has two series of subscripts. Why? There must be a difference. Why are there more series of subscripts? Okay, so to specify the algebra in one of the papers, Keller wrote, this is a Clifford multiplication plus that's already an extension. He uses differential coordinates. I don't like that. One can do better going towards in the direction of less coordinates and so on. But I'm just telling you what he did. And the type of structure we are going to build is the one defined by a metric and only a metric. So this is original Riemann geometry. But something, according to Cartan, very, very important, happened in 1917. So that Cartan distinguishes very clearly about the Riemannian geometry before 1917 and after, to the point that he refers to the Riemannian spaces of before 1917 as pseudo spaces, not Riemannian, not pseudo Riemannian spaces. That's another concept, but Riemannian pseudo spaces, because there was no concept of equality of vectors. He introduced a vector space. The curvature was solved by, or found together by, independently by Riemann, Christoffel, and Lipschitz as a problem of equivalence of quadratic differential forms, symmetric quadratic differential forms. I will not call a metric, a quadratic symmetric differential form a metric. I will call a metric an equivalence class of all those quadratic forms that can be obtained one from the other by a coordinate transformation. That was the problem of Riemann. The big question, whether we can convert one quadratic form into another, and specifically to the Euclidean one. Whether if I'm given G mu and of x dx mu, whether I can reduce that to a sum that may or may not be possible, and in order to know whether it is possible or not, we construct the Riemannian curvature.
On the right is tensor, on the left is scalar?
No, okay, first of all, it's not my fault that people who are writing this, they should do that. And here, we will have we are interested in this animal. Cartan told us that in order to solve equality problems, first we find a set of differential log forms that are related to that. In general, G here will constitute a basis of differential forms. But normally I will not need general basis of differential log forms in the module spanned by those animals. But of particular importance, very relevant here, are these which are canonically connected with this. Namely, what did you forget? From 1 to the dimension of the manifold. So our structure is simply a manifold where this animal is defined. That's all we have. We are going to have tangent vectors. We don't care. So I'm talking later on to connect the differential forms that have been
This
defined.
X and G, and the X hit this one is B.
Well, I think there's one
Yeah, but so the same as over there?
that over here.
No, the next line. So we have G, some energy.
G means function of all the coordinate space. Function of the coordinate you wish.
I don't understand.
All right, okay. You've seen this in the literature, right?
Yes.
Okay, that. So at the end we can discuss anything. All right. So these elements are very important. Why? If I give you this metric only 2, and let's say what are the omegas that satisfy that? You're going to say, aha, omega 1 equals dx, omega 2 equals dy. That's only the beginning. In reality, there is an infinite set of them. So omega 1 in general will be as general as cosine theta for theta dx minus sin theta. Is that theta? Theta or what is it called? Whatever. dy. Sin theta dx cosine theta dy as omega 2. That's very important for 2 reasons. For one, I say that I can give the metric as d rho squared plus rho squared d theta squared. I have 5 then here. So that is the same metric by my definition. So what are going to be in terms of this system, what are going to be those omega mux? Well, we know that d rho and rho d5 satisfy that this square, is the domestic. But again, the same game. So instead I use cosine lambda minus sin lambda, cosine lambda, d rho and rho d5. Now we look here and we see anywhere coordinates. So well, your approach is coordinate dependent. No, I'm using coordinates, but it is not coordinate dependent. Why? Because when I'm making about all things here, all lambdas, meaning that for each theta, I have 1 lambda. If I were doing differential geometry and tangent vectors, I would be saying that this belongs to the boundary, this belongs to the boundary, the boundary is only one for a particular problem. If that comprises of the frame, that will comprise also of the frames. So there is a one connection between this and that. All right. omega list of the x's and of the dx's, but also on some additional coordinates. Those additional coordinates being introduced here, the additional coordinate is 1, but if I have already mentioned, okay, I will have the matrices depending on 2 parameters. So, this is extremely important. Now we see why. But I'll keep the order because there are some very writes components. I don't like the usual components because it's too many components, but too few I will do either. A, those are going to be components of mu sub 1 up to mu sub n. P sub 1 up to P sub P. And lambda sub 1 all the way to lambda sub n. Why 3 series of indices? What are they two for? The big issue is here. Why 2? Okay. Professor Campo has talked about linear functions of vectors, and we could have at different points that we have a field of linear functions of vectors. And that is, at one point we have the dual space. At many points, okay, all over the manifold we have as many linear spaces of that type as points on the manifold. But there is something else. I want to compare animals with this part P with animals with series of numbers or series. As an example, I'm going to take the curvature. The curvature is an animal whose components will lower and raise components and indices, but that comes later. Originally, the curvature is an animal which invented whose components are, for the moment, I want to relate that. So this is going to be a mu, this is going to be a pi, and this is going to be a lambda 1 and lambda 2. Since I don't like to work with components, I'm going to complete the picture and say, this is going to be some basis of, I speak not only about 5 because delta has to be, we know pi e mu omega lambda 1 omega lambda 2. I'll tell you where it comes from in a minute. So, 2 series of indices or subscripts. What is this? And what is this? In Keller, these are going to be functions of 2 surfaces. And these are going to be linear functions of vectors. Let me get a very nice example, simple example of where the curvature comes from. Because normally you take a look at differential geometry, and at the end you will know what that is for. The curvature. Suppose, let me start with a Euclidean space, because yes, excuse me.
I don't understand this part. I'm trying to understand that. I don't understand why do you use the rotational with the...
Okay, because the rotations, and only the rotations, are the transformations, okay, which leave invariant the form of the dx squared or the dy squared. What I'm saying is that if you form the square of I said that from here I read, if I form the square cosine theta dx minus sin theta dy, square of that, and I add similarly the square of sin theta dx plus cosine theta dy, you operate and at the end what you get? Dx squared plus dy squared. Have I answered your question? Thank you. Alright, so assume you have a vector field in, and we differentiate. This is a zero form. Vector value zero form. So this will be a vector value one form. If I differentiate twice, never mind that it is going to be zero Euclidean space. This is going to be a vector value. Okay? Differential form. Where is the curvature? Well, it happens that if I develop these, I get this. But this is an element of the basis. This is an element of the basis of differential forms. But these are just numbers. So this is not yet the curvature. The curvature, I obtain this when I do this operation, I obtain that. It happens that those become zero. Fine. Not in general. So I am going to define the curvature as where this is a basis, element of the basis of linear one form. So that when I evaluate that on the vector field D, I get what I had before here in D1. So that is the difference. And whatever this, these are not anti-symmetric bilinear functions of vectors. These are functions of surfaces. Now, what is this geometrically? I have a vector field here. Okay, I move it to this point and then from this point to some other point. I started with a vector V here and I end up with this one with another one. Okay? But now I'm going to go to the same place through another path. And I end up with a different vector. Okay? That VDV, when I am not in a Euclidean space, that VDV is precisely this little difference. It depends on what vector I started with. It is going to be a vector, so that will be a basis. And what is this? This is this. Okay, function of surfaces. What surface? This surface. So, that is, there you have two types of subscripts. Take dr. In the literature, dr or db sometimes are called. dx mu, I don't like that. Okay? I prefer to write on value. What types of people? This would be actually, because of this, it will be vector value, because of this, it will be a differential one form, so that is a vector value differential one form. If I write it in terms of the basis of differential one forms, and for those, this is actually say mu delta, canonical delta, mu lambda. Now I am not paying any more attention to the what I have labeled the indices, omega mu e lambda, and when you sum over indices, this is this. So this will be the unit, this will be the unit vector value one. Okay. Now, so the differential forms, okay, in Canada we have to distinguish between field of bilinear functions of vectors, well, let me start with a field of linear functions of vectors and a differential one form. A differential one form will be a function of curves. A linear function of vectors will be a function of vectors. But since I have many vector spaces over a curve, well, at each point it is a field of linear functions of vectors. Not to be confused. I don't want to. So what is the x here, according to this? It will be a function of curves. And notice I shall be using Stokes' definition of something. There are members of this audience who do not like the concept of theorem, use the term Stokes' theorem. I said it is going to be a function of curves. I observe gamma between points A and B, or maybe gamma for A and G, or I don't know what notation you like, such that upon integration, that is the x. Alright, but on me, it is not that Dracula doesn't exist. You don't understand.
It's exactly the same.
Hey, one second. One is a linear function of vectors, okay, and it depends. If I have a vector, thank you for the car, because if I have a vector here and the tangent vector there, in order to compare the vectors, I need to have a connection. Whereas here I don't need a connection. That is the big difference. So, in this, okay, I'm trying to explain it clearly. Okay, in Tomraf, this is irrespectful. Because, okay, I know what the book says, but I'm not interested in that because differential geometry since 1930 hasn't gone nowhere. Okay, except for the one of ours, this guy. The non-commutative one. Okay, because quantum mechanics, in a few pages, is going to get to the hydrogen atom. Okay? Thanks to this calculus just by studying an equation. Alright, so this is scalar, which is far above us in the history of mathematics. Alright. There is a very important connection between the two. So, okay, according to this, if I is going to be minus, if I have EI equals OEIJ, EJ, this is connection dependent. We are going to have if I is going to be minus omega Ji phi j. And that is the difference between the two. This is connection dependent, this is connection dependent, and now what do I want to put there? I don't need to know about the connection at all, because exterior differentiation does not depend on connection. So that is the big difference. Now,
you did not the same letter. You did not buy the same letter.
I don't want to use the same letter.
Depending on small d, sometimes is.
Very good question. Okay, what about the d?
Because Akarpov denoted by small d, totally different concept.
Why? Why did you become the same? Okay, what happened? The very beautiful thing for me of scalar is that all the negatives come together. And then one which keeps the airways as that, includes airways as that. Okay, they come together. So, exterior covariant, interior covariant is not in the literature, and that is even Lie differentiation. Even Lie differentiation. So, and this one is going to be exterior covariant or something else, and this is going to be solve. Now let me go to what invariance can I, differential invariance, can I obtain from an expression like this? Or equivalently from this. Remember that the obvious in which I'm interested, the one who sum the squares give us the metric, are functions of the axis, the d-axis, and some of the animals lambda. And they are differential one forms. What happens if I can differentiate this? And I can write these are two forms in principle, but you think, aha, they can be combinations of terms of this type with this, terms of this type, and terms of that type. For different, but in general, we look at this, because here, there is always, if I differentiate this, there are always going to be dx's once or twice. This dx, but the one from differentiating this. But there are not the d lambdas, this is one, y, this, but I'm going to get a linear combination of those with those, but not those. They don't enter the picture because of that reason. Okay, but I can always, okay, instead of writing here the extreme differential forms, one forms which are depending on the system, I'm going to use the omegas, which are one forms, and I'm going to form a linear combination, and I'm going to pay attention to the details. I'm going to put everything in there. This does not define those, because you can add to those omega-j's other things such that when contracting the omega-j's, they give zero. But canonically, Cartan, 1922, in the given page, showed that this is in modern times what Kronecker and Lipschitz and Riemann solved, because the components in terms of the dx's of these animals are nothing but the Lipschitz symbols. The Lipschitz symbol will be Christopher symbols. Okay? Now, to differentiate this, but to obtain this is a little bit of complicated argument in Cartan, because on the one hand we have a tensor structure, and on the other hand we have an exterior structure, and only somebody like Cartan can manage the two at the same time. Okay, and so it is not an easy proof, but when we look at it, then eventually we derive that with the character. But this is canonically, this system is canonically determined by the metric. And we don't need anything else but the metric. So we can do vectors, we don't need linear functions of vectors. If my problem, if I start with this, what if I start with geometry? There is no cutting vector, no whole face of the three linear. The different matter is that, indeed, using tangent vectors, dependent to this expression. Originally, algebra was in very raw, primitive state in the middle of the 19th century, and they were not dealing the problem of Riemann geometry was not a geometric problem, but it was a problem of equivalence. In fact, the curvature was derived by Riemann in a paper in response to a competition by the French Academy of Science or Mathematics, whatever it was, on a problem of heat transfer, which he solved by converting somehow that problem into one of solving the equivalence problem of metrics. Okay, now the difficult, excuse me, now I go to the Keller calculus. Keller, when we put, remind me, when in the next talk or the second next talk, we put there one of the chapters I wrote on differentiation, chapter 3. At some point, what I did is to copy the formula that with which Keller shows the differentiation of a general line whose components have those three series of indices. Okay, it is a very complicated equation, and it doesn't say where it comes from. Has that been your experience? Okay, my interest is in showing how it relates to all this. And for that, okay, the omega mu equals omega mu. Now, that we are going to remember that. I should not less. Now I'm going to go to Keller's differentiation. He is going to define his differential. Okay, yeah, his general differential in this form. This is going to be the sum of the exterior derivative. This is going to be a differential force in the Keller algebra, which then, since it was quantity with three series of indices, that means that he has a product of three tensor product of structures, three different structures. Here we are only going to care of the three series of indices. We are going to care only of those ones. This will be for contravariant vector fields, this for covariant vector fields, or maybe the name is the other way around. But we are not going to be interested in those because there is more than enough to bother to see to do that. So, plus.
Because this first small d is of course connection dependent. This
okay, this d, it depends on whether u is tensor value or not. If this u is not tensor value, but a scalar value, this is the one that satisfies the d universal. He is defining if this is scalar value, then we have this. If it is vector value or tensor value or infer value, then this is not going to be satisfied. Because
Christopher, the derivation of differential form is not the same as exterior derivation. No, but you say that it is.
No. The point is that there is one derivative, one, so to speak, a general derivative together. Okay. Then the meaning of the operation will depend on what I am acting, or what I'm acting on. Alright? I have two children. Say one is 3 years old, and the other one is 15 years old. They have misbehaved, they have committed the same. I'm going to reprimand them in a different form. Reprimand. Okay, I'll continue. So, if we have 10 paralysis, even if I had a correction, this would also be 0. But in general, this is not, dd is not 0. Observation, in the literature, even Cartan will write this. This is not correct in general, but from the perspective of integration of differential systems, it still makes sense. But I should write in general like that. One symbol, not two, until the system of differential equations is, I find that it is integral, at which point I can go from this to that.
For example, something is impossible, because if u is differential function, as was
yes, scalar value.
Scalar value. What is value of your d on df?
On df?
If u is df, u is differential of fs.
If I write it in terms of coordinate basis of differential,
just u is differential function.
u is f.
Is equal differential of function.
Oh, thank you.
Yes. What is your second? No, but if the second D is Christopher, and Christopher does not commute with.
We go to Christopher. Christopher is not a primary concept that we can write now if we just wait. We'll see what Christopher is. Why? Because Christopher is going to enter here. But the primary concept is going to be, okay, this. We are given this, we differentiate that, and we don't know Christopher. Okay, and we are going to find Christopher. So I'm going to, first I have those. I'll differentiate them. I differentiate them.
But if omega mu is differential function, what it means?
Oh my God. If it is a differential function, what you learn in the school, and you know it from your dream. And if you differentiate it again, that's zero. Forget about Christopher. For the time being, you don't have Christopher until you have something like this. Okay? Christopher has three series of indices and so on. So then you continue and you run it. Wait in a minute, because now it's when it becomes very interesting. If I know this, I don't know that. Because for this, I don't know also this, which is like the derivatives. But now if I know this, and I am given a metric plus a metric, there is a canonical this and a canonical that. Okay? And that canonical thing, whatever it is, that word Aristotle signals come in. Can I do that? Because here is what I want you to have from today, so that you don't commit a certain mistake. Now, Keller defines his, because I already do pieces, but in the following form. Unfortunately, he uses a coordinate basis of differential forms. Not my fault. I'm reproducing what he does, and immediately I move to a more Cartanian version of it. He does this. Now, this is called frame dependent, but all this is not again. We have a type of product, so that can be written as the exterior product or the dot product. This is going to be the exterior derivative, and this is going to be, we call it the interior derivative. But watch! It will look, once we have reached to this point, when we say, aha, if I know what is this, I obtain this and I obtain that. Fortunately, this piece does not depend on connection. So, what I'm going, this is going to be first. And from there, I'm going to, if I have a metric, I'm going to canonically determine this. Alright? So, if you give me a function, I can obtain the gradient, but I can, or you give me a vector field, I can obtain the curve, but I cannot obtain the gradient. Well, you don't get the curve because of the dual linear functions, the dual, this is wrong there. Okay, so the du, the du then is dx mu exterior u sub mu, okay? Where this is what can cause the covariant derivative of g. Instead of u, I put the omega mu's canonically determined by the metric, I mean those, then I will have d, now I'm reading here, d omega mu equals omega mu, stereo omega mu. Omega, okay, instead of u, I have omega, something new. I have to put d subscript mu, okay, omega mu. So, repeat. From the definition of the exterior derivative, okay, I have the contraction with the exterior product of the basis of differential one forms with what we have called the covariant derivative. But what is the covariant derivative? That's the correlation, that's the definition. I'm going to, by comparing this with that, I'm going to obtain the covariant derivative. Someone will say, aha! There, I got it! Wrong! This is true, and this is true, but that doesn't imply that this is equal to that. Why? Because this will still be undefined by quantities such that when I contrast them with that, it is zero. So, in order to obtain the right results, what does one have to do? I write this as some compass. What is gamma d omega mu equals, where am I? I'm here. I can, these are the form gamma mu omega mu, or use omega lambda. And these are going to be also of the same type. So, in order to get to this, I am going to play with this. It is a game. There is one obvious game. which is this equal to that, but there is another game, which is the factor, this factor, instead of getting it just by reading here, I can develop this and obtain that factor from it. This is a differential one form. In order to say this is this, I could do the alternative. We haven't computed the numbers, but I assume also you who are studying a little bit of differential geometry, okay, you know that the solution of this is the Levi-Civita forms whose components are Christoffel symbols. This will be the Levi-Civita forms. Okay, gamma, mu, omega, lambda. And now I'm going to redistribute this. I'm going to put this at the front. Since I changed those two, I have to put a minus sign. And I'm going to say then that my this is going to be that. And the minus sign appears. Now, warning. When I work with orthogonal bases, it happens that there is this anti-symmetry, which goes, okay, if I write omega mu as gamma mu lambda, omega lambda, okay, these are not the Christoffel symbol that you got in the tensor calculus, which involves the derivative of the metric. And the metric, okay? When you use orthogonal bases, you have this anti-symmetry property. But when you use coordinate bases, you don't have that property, and instead you have symmetry with respect to this pair of indices. So what? If I will use this one, is totally general. It will work for coordinate bases, for orthogonal bases, or for anything. This one is only for orthogonal basis. If you have coordinate basis, you have to have here d, he, mu. Okay, so then the covariant derivative of omega mu, let me repeat it. That the omega mu is going to be minus gamma eta, well, here, maybe I'm using too many indices for the minimum, and this eta that is, what should I tell you this eta? So that is the only thing what we have to remember, okay, which I get from the process. What has been the process? From what is the first equation of the structure, I have written in terms of the basis of one forms, these one forms, that basis, okay, and then I have changed the role of the two, so that the subscript over here, I get it, yes, this goes with that, this goes with that, and this goes with that. So it's easy. The process that is easy, you don't have to remember the complicated formulas of Kerr. Okay? You just do this, span this, exchange the two, and take the index here and ask the subscript here.
So you assume the torsion is zero or not?
Pardon me?
Do you assume the torsion is zero or not?
Torsion is zero because it does not even enter the picture. Because I said my only structure is going to be the quadratic differential form.
If torsion is not zero, how to modify?
It doesn't, you don't modify anything at all because we are dealing with scalar value differential forms. So I can tell you what the torsion comes from. Or listen, Stephen, you could have just a metric. I'm going to start simpler than that. We have Euclidean space. We have affine space. On how many coordinates does it depend? And that what is matter? Remember what I did here of obtaining the most general differential one forms. If I am in geometry, geometry only starts according to Cartan, of course, this is a matter of taste. But for these purposes, when you have tangent vectors and connect them, here we have an affine space defined based on n plus the affine group on n plus n squared parameters. True or not? So, a manifold which infinitesimally, so to speak, okay, is affine is going to depend on n plus n squared differential one forms. N plus n squared. That means that the omega mu's and the omega lambda mu's that represent an affine connection are going to be n plus n squared independent differential one forms. Here I am dealing with the structure that one can derive by having only those. If you have these plus those, from just from that we are going to get Christopher Seaworth, etc., and the Riemannian curvature as a problem of a solution to a problem of equivalence. So you can always ignore that to obtain certain things, and you obtain the Riemannian curvature. But if you get this and that, you can also obtain what is called the affine curvature, that should be called in reality the Euclidean curvature. And they are different. And the big mistake of Einstein in the late 1920s, when he wanted to create a unified theory, the big mistake was that he said, okay, I'm going to make the curvature equal 0 and ignore it. That is wrong, because in addition to, you can make this curvature equal 0, but you still have the Riemannian curvature, which only depends on the metric and not on the connection. Okay, so you cannot bring in the torsion, because the torsion comes only when your structure is defined by the differential forms. These and these independently. Then the torsion appears. How? Sorry. How? D omega mu minus omega mu, if those are independently defined, then when you form this is not going to give, I'm talking to you, this is not going to be 0 in general, because these and those have been independently given, and that gives rise to the torsion. But as I said at the beginning, I am talking about the structure, original structure defined simply by this. And then I have gone to modern things according to Cartan, of which ways, things for which purpose I introduce those omega heights. But in the most general form, okay, after applying that group which leaves the metric invariant. I think that I should stop and we can speak about it.